Thank you everyone for coming to this data science and computational statistics seminar. It's my great pleasure to introduce our speaker, Aretha Teckentrup. So Aretha did her PhD in mathematics at the University of Bath in 2013, which is followed by postdoc positions, firstly at Florida State University in the US, and then University of Warwick nearby. He then joined the University of Edinburgh in 2016 as a lecturer in mathematics of data science. And Aretha, you can share your screen and make a start.
Yep.
Thank you very much. And by the way, if you guys have any questions, please leave them in the chat box unless it's very urgent. And Aretha will pick them up later on. Thank you.
Okay. Yeah. Well, thank you very much for the invitation and the introduction, and thanks everybody for coming. So what I want to talk about today is some recent work on Gaussian process regression, and I mean the three things: convergence, robustness, and flexibility. Hopefully, that will become clear throughout the talk. What I mean by those things. So the outline of my talk is the following. So I'm going to start just by introducing the problem that I'm interested in solving. So the problem formulation. I'm again going to describe how you can solve that problem using Gaussian process regression. So I'm going to go through the methodology, the general setup, and how that works. And then I'm going to be interested in these two things here. So the first two are kind of the introduction and the setup for everything. And then the last two sections are more about recent research. So there's a section on the kind of convergence properties of Gaussian process regression. How well does this method work? And in particular, we're going to be looking at some robustness of this methodology. And then in the later section, I'm going to be talking a bit about deep Gaussian process regression. So how you can use deep Gaussian processes in this Gaussian process regression framework. Right. So the problem that I'm interested in solving is this one here. So I have an unknown function f that maps from some domain U into the reals. If you're interested in multivariate functions, then you can also deal with that. For simplicity here, I'm just looking at a real valued function. So there is this unknown function f, and you want to kind of recover or learn what that function is from observed data, and the data that you have is this y, which is some function evaluations of f. So you have some points un in the domain of f, and you have the corresponding function values f of un. You have a finite number n of those, and then from that you want to reconstruct what the underlying function f is. So in this talk, I'm going to assume that there's no noise in the function values. You can extend everything to the case where you have noisy function values as well. And if you're interested, I can point you to a reference at the end. So this might seem like a very simple problem, and maybe also a bit boring problem, but I can hear that one, it's not an easy problem to solve. So this, in full generality, this is actually a very difficult problem to solve if you don't really know anything about the function f, and the function f can be completely arbitrary. Then it's actually very difficult to develop methods for this that work well. Right? So the f could be, for example, a multi-scale function, or it could have very steep gradients or things like that. So getting that to work for a general f is actually quite complicated. And it's also an important problem. So a lot of the problems that appear in machine learning, for example, can be essentially reformulated as a problem of this type. So if you think of, for example, having this set of training data here, which are the input and output pairs, un and fun, if you then want to predict the outcome for a new value of the input, that essentially means that you want to learn what f is, and so things like prediction and classification easily fit into this framework. Okay. So that is the problem. I'm going to be solving it in a Bayesian statistical framework. So in that framework, the solution that I'm going to get is a probability distribution, which is called the posterior measure on f given y. So because I then have a whole probability distribution on my unknown function f given the observed data, that allows me to also do some uncertainty quantification in the recovery. So I'm going to have some information about how, firstly, what I think the unknown f is, and also how sure I am about my recovery, right? So you can use the variance of the posterior measure as a measure of how certain you are about your recovery. So one particular question I'm going to be looking at is what is sometimes referred to as posterior consistency. So this is essentially looking at what happens as the number of data points n that you have tends to infinity. So intuitively, as n tends to infinity, right, you get more and more information about your function f, and so you should be able to recover f more and more accurately. And so that's what we hope is going to happen, that as n tends to infinity, you kind of converge to your true function f. And the way that you can measure that in this Bayesian framework, when you have the posterior distribution on f given y, so you can look whether the mean of this posterior tends to the truth, and the variance of this posterior goes to 0. So you kind of converge to a Dirac delta distribution on the truth. So you kind of concentrate on the truth. So that is the problem that I'm interested in solving. As I said, I want to do this in a Bayesian statistical framework so that I get some uncertainty quantification. And Gaussian process regression is really just a particular instance of the Bayesian statistical framework. So it is a particular choice of the prior distribution. So you do the standard thing that you do in Bayesian, in the Bayesian framework, that you choose a prior distribution on your unknown f, and then you get the posterior just by conditioning on the data. So here we're now choosing a Gaussian process prior on the unknown function f. If you're not familiar with Gaussian processes, I've given the definition here. Right, so essentially what that means is that at each point ui in the domain of f, you now have a Gaussian random variable. Each finite connection of these points follows a joint Gaussian distribution. The two things that you have to specify are the mean function, which gives you the expected value of the mean at every point. And then the second thing that you have to specify is it's called the covariance kernel, which gives you the covariance between your Gaussian process f at two different points, ui and uj in the domain. So that is the mathematical definition. I'm here choosing mean 0 for simplicity. Everything can be extended to non-zero mean as well. And again, I can give some references in the end if you're interested. So that was the mathematical definition. More visually, you have something like this. So you choose a mean function, which in this case is chosen to be the 0 function, which is this black line. And then at each point in the domain, my f is now a Gaussian random variable with this mean, the black line, and then some standard deviation. And so if I sample from this Gaussian process prior, I get functions which look something like this. On the left, you get functions which stay close to the mean and then fluctuate around the mean with a size that's proportional to the standard deviation that you've chosen. So you get something like this. But all it really is a probability distribution defined on functions. Right? So as I said, then to get the posterior distribution, you do the standard Bayesian prior to posterior update. So you take your prior and condition it on the data, and the data here is these function values that we have observed. The nice thing about Gaussian process regression is that you can do this conditioning explicitly. So the conditional distribution on f given y has an analytic formula, and you can write that down explicitly. You know that it's still a Gaussian process, so you can have a Gaussian process distribution with explicitly known mean and covariance. And so I've given you the formulas for the mean and the covariance here. What exactly they are not that important, but it's really just important that you know what they are, and you can write them down explicitly. Yeah. So when you do this conditioning, you then get an updated Gaussian process and an updated mean and covariance. And so here, for example, when you've observed these data points that are indicated by the black dots, your mean function gets updated to this, and it goes through the observation points because you're conditioning the process on going through those points. And similarly here for the sample paths, again, because you're conditioning the Gaussian process on going through those points, you do get sample paths that go through those points as well. Right? So this is then your updated distribution on your unknown function f given the data y. And so you get this distribution here, which at the black points, you know what it is because you have observed those points, and then you have a probability distribution on what you think f looks like in between those points. Right. So that is all Gaussian process regression is. So one of the challenges that you have, which is a kind of a very common challenge in the Bayesian framework, is that you need to be able to choose a good prior. Right? So once you've chosen the prior, you can just do this prior to posterior update that I've shown you, but you do actually need to be able to choose a good prior for this problem. And I mean, in general, you have to choose a prior that kind of has the properties that you think your unknown function f is going to have. So it needs to kind of reflect the properties of f. And so what do I mean by properties here? I mean things like I've listed here. So in particular, because we're assuming we have zero mean, everything is determined by the covariance kernel, and the covariance kernel is going to determine many different properties of the Gaussian process and what kind of properties the sample paths are going to have. Yeah. So for example, there's one property which I call here smoothness. So what I mean by that is differentiability. So how many derivatives sample paths of the prior are going to have in terms of the input. So I've given you some numerical examples here in the figures. So each figure shows 5 independent sample paths from different Gaussian processes. In the first row, I've chosen a covariance kernel that is not very smooth. So I've chosen, for those who are familiar with the area, I've chosen the exponential covariance kernel. There's the covariance kernel of the Ornstein-Uhlenbeck process. And then you get sample paths which are not even differentiable. Whereas in the bottom row, I've chosen covariance kernel, which gives you analytic sample paths, so sample paths that are infinitely many times differentiable. So that is for the Gaussian covariance or squared exponential covariance, for people who know what that is. And you can see they look a lot smoother. The kernel also determines what I call the contrast, that is the kind of size of the amplitude of the function. So in these graphs, whether you kind of go between -4 and 4 on the y-axis or between -40 and 40, so it's just the size of the amplitudes. There's also typically a parameter in the covariance kernel that determines the correlation length scale, the length scale fluctuations. So that determines whether your function f is kind of quite smooth and only varying on long length scales, as you have in this figure, or whether it's varying on kind of shorter length scales, as you have here. And so the left column is Gaussian processes which have kind of a long correlation length scale. So the lambda here is large, and in the right column you have Gaussian processes which have a short correlation length scale. And you can see that they are much more oscillatory. There's also things like periodicity and stationarity, which are determined by the kernel, but I'm not going to be focusing too much on those at the moment. Okay. So the problem is that you typically don't really know what kind of properties your function f has, right? So you don't know what f is unknown. All you have is the function values y that you have observed, and whether your function has kind of a short length scale like this or a longer length scale, whether it's smooth or not smooth, is something that you might not really know a priori, right? So there's typically some hyperparameters theta that are in this kernel that determine these properties, and you don't a priori know what good choices for these hyperparameters, what the kind of best choices for these hyperparameters are. So you somehow need to have a methodology that allows you to incorporate that, and to kind of have a methodology that allows you to kind of learn what the hyperparameters theta are. So if you do a full Bayesian approach, then what you would do is you would find the joint posterior of your unknown function f and the unknown hyperparameters theta given the observed data. And then you can get the margin, the posterior that you're after on your unknown function f, just by integrating out the theta, so just by getting the marginal distribution of this joint posterior, but that is quite often intractable to do in practice. So what is often done in practice is this empirical Bayes approach, which is also called a plug-in approach. So what you do in that setting is that you use the function values that you have observed to compute an estimate of the hyperparameters. So from this, you then estimate good values of the hyperparameters. So you estimate what you think, for example, the typical length scale of fluctuations is for your function f. You estimate that, and then you pretend that that is kind of the true value of the hyperparameters. So you then take this value and then just kind of plug that in as the value for the hyperparameters into the prior, and then you just do the standard prior to posterior update. So the question that I'm then going to be interested in the next couple of slides is how that kind of influences what happens as n tends to infinity. So in particular, as I said, what we're hoping is that as n tends to infinity, we kind of get convergence to the truth, so convergence to the true underlying function f. And in particular, if we don't know the values of theta, but we have to estimate the values of theta, in particular, the estimate then also changes with n. How does that kind of influence what happens as n tends to infinity, and do we still get convergence to the truth? So how you actually estimate these hyperparameters is a difficult question on its own. So I'm not going to be addressing that question too much. There's still research going on there, how you can do that efficiently, but you can use things like, for example, maximum likelihood or maximum a posteriori estimation or cross-validation or something like that. So the results that I'm going to show you are don't assume any particular method of estimating the hyperparameters, and it can be a general method. Right. So as I said, what we're now interested in is looking at what happens as n tends to infinity. And particularly, we want to show that our posterior measure on f given y kind of converges to the truth, right? So what that means in this context is that the mean of the posterior, which was this function mnf, so the mean of the posterior tends to the true f, and the variance of the posterior goes to 0, right? So your posterior measure kind of gets more and more narrow, concentrating just on your true function f as n tends to infinity. Okay. So to prove that, we're going to use some results from numerical analysis. So you can make a connection to scattered data approximation and numerical analysis methods. Okay, and that's then going to be helpful to get some convergence estimates. And so to do that, you essentially note two particular properties of the mean. So for the mean of our posterior, the posterior mean, you know that at the design points un, you just obtain the true function f, right? And that is simply because we are doing the conditioning. Right? If you think back to this part here, the MNF is the black line, because we're conditioning the process to go through our observed data points y. We kind of have an interpolant going through the data points. Right? So that is this expression here. And then if you, as I said before, you actually have an explicit expression for this mean, you can write it down explicitly, and you can in particular write it down in this particular form as a linear combination of the prior covariance kernel. Remember, K was the covariance kernel that you chose for the prior in Gaussian process regression you just get this linear combination here where the constants alpha are known. Right? So what this means is that you just have an interpolant of f, which is what's called a kernel interpolant. So it just means that it is an interpolant of f, and the basis functions that you're using are these kernel functions, right? So the kernel functions k, u, u, n here take the role of the kind of basis functions that you use. And in particular cases, you then get what's known as a radial basis function interpolant, where the kernel function k only depends on the distance between the two. So that you get that for isotropic kernels. Right? And that's a method that's very well known in numerical analysis. Yeah. So because the prior covariance kernel k takes the role of the basis functions in the interpolation, the kind of error estimates that you get, in particular what kind of rate in n you get for this convergence, will depend on what kind of kernel you choose. There are results out there for a wide range of kernels, and they are very general results. So whatever your favorite kernel is, there should be a result there that gives you a rate of convergence. What I'm going to do now is I'm going to show you one particular example for the kernel k. So that's a kernel that's very often used in applications. So that's this family of Maternal covariances. It has this quite complicated expression here. Okay. So the important thing is that it has three hyperparameters. So the hyperparameters theta that I was talking about earlier, and are these three parameters: sigma squared, lambda, and nu. Sigma squared is the marginal variance parameter. This is the contrast. It's the what governs the amplitude of fluctuations in f. Lambda is the correlation length scale. So if lambda is very small, then you get very oscillatory functions that vary on short length scales, whereas if lambda is large, the function only varies on longer length scales. And then the last parameter is this smoothness parameter nu, which governs how many derivatives your function f is going to have as a function of u. Yeah. For some cases of nu, the expression simplifies. So this quite complicated looking expression simplifies substantially. So for example, for nu equals 1/2, you get this exponential covariance function, which is the covariance function of the Untitled process. And then the limit as nu tends to infinity, you recover this Gaussian or squared exponential covariance function. Okay. So for this particular covariance kernel, you have this result here. So I know that this result looks very complicated, and I don't think I'll be able to talk about everything. So let me just try and give you some of the main features. So this is a result for the Maternal covariance kernel. We have the hyperparameters theta here, and as I said, the theta here is an element of R3, and it contains these three parameters. You have the sigma squared, lambda, and nu. And this is a result that shows convergence of the posterior mean with the estimated type of parameters to the true function f. So this right-hand side will typically go to 0 as n tends to infinity. And likewise, this right-hand side here will go to 0 as n tends to infinity. And so this then shows that the posterior variance, this was the posterior variance with the estimated type of parameters, also goes to 0. Okay. The way that the dependency on n, so the number of design points or interpolation points, comes in is through these two quantities, h and rho. So h is what's called the fill distance. I think in statistics it's also called the maximum distance. In numerical analysis, I think also sometimes the separation radius. So it has a couple of different names. But it's essentially measuring how well your design points un are covering the domain of u, right? So the domain of f. Right? So remember, capital U was the domain of f, and so you're looking at how far any point in the domain of f can be away from your interpolation points. Right? So in particular, if this fill distance is going to 0, that means you kind of have a space filling design and you're covering the whole domain of F. Typically, the rate that you get is n to the -1 over the dimension. So that's what you get here. So this is what gives you the convergence, and this is what our intuition kind of was telling us, that as n is increasing, you have more and more information about F, and so you should be able to recover F with more accuracy, and this term here will go to 0 as n tends to infinity. The rate that you get will depend on kind of the true smoothness of F. So the new here, I'm assuming that F is in this Sobolev space. So if you're not familiar with Sobolev spaces, essentially assuming that my function F has this many derivatives, so nu plus du over 2 derivatives that are square integrable. So the smoother F is, the faster you converge. And then it also depends on what your estimated smoothness is, right? So the nu star here is kind of the estimated smoothness. Yeah, Hong, you have a question?
So you do not know F, right? So how do you know that? How do you know the norm of F, or how do you know that F belongs to that?
Yeah, so this
space?
is just an a priori error estimate. So it's not an a posteriori error estimate.
I see.
Yeah, so this is purely a theoretical result that tells you that as n tends to infinity, you should expect the error to go to 0, but you're not actually able to compute this error bound.
I see. Thanks. Right.
Yeah, I also have a question. So in your convergence result, I probably have mentioned this, but I might miss it. So I think it may depends on how the samples are generated.
By samples, you mean the design points?
Yes, the design points.
Yeah.
Yeah.
So this result actually holds for any design points. So no, it only depends on the fill distance. Right. So that's a nice thing about this result. So there are other results out there that are specific for specific set of sampling points or design points. But this one is actually completely general. So whatever your points are, you just have to compute the fill distance and then.
All right. So, but is there any conditions for that, like how you actually generate the design points? For example,
yeah. So for this result, there aren't. So I mean, the bound that you get here, so this less than or equal to, holds whatever the dn is. But if your dn is not chosen well, then this error bound is just not going to tell you anything. So it's not going to be a good error bound if you don't choose dn well.
Yeah, thank you.
Does that make sense, right? So for example, if you don't choose the sampling points to be space filling, so if there's kind of a part of the domain that you're missing out, then this fill distance is just not going to go to 0, right? So this term is not going to go to 0 as n tends to infinity if you don't. So that's kind of how the choice of sampling points comes in.
Thanks.
Yeah. Okay. Were there any other questions at the moment? There's something. Chat maybe. No. Okay. Yeah. So as I said, this is a quite complicated looking error bound, probably. So let me just kind of go through the main points again. So the only assumption that you need on F is that it is in this particular function space, so this Sobolev space. You need to assume that your F has a certain number of derivatives. You don't have very strong assumptions on the estimated type of parameters. So for this particular result, you need the estimates of the parameters to be uniformly bounded from above and below. You don't need them to converge. So I've written down the simpler case where the smoothness parameter does converge. If it doesn't, then you can work with the lim inf and the lim sup. The estimate gets a bit more complicated. If these estimates actually are not uniformly bounded, so for example, if one of them would converge to 0 as n tends to infinity, you can also include that. So that would go into this constant here, and then you would get some more dependence on n through there. I'm happy to talk more about that if people are interested. As I said, from this, you can get some rates in n. So if you, for your particular points at dn, if you then kind of work out what everything is, you get some rates in n. In the best case, you get this. So this is the fastest rate that you can get. For example, you get that when you're estimating your smoothness parameter exactly, and the rates that you get are actually optimal. So they're optimal in the sense of approximation theory, that if you have a function f that is in this Sobolev space, and you approximate it with any linear method that's based on n function values, then this is the best rate that you can hope for. I haven't talked very much about this other term that involves the rho. So this is something that is due to stability issues. So this is actually something that is not decreasing in n. In the best case, it's just constant, but it can also be increasing in n. And so you can kind of chip off a bit from the convergence rate that you get from the first term if you run into these stability issues with the rho here. So the rho is, well, it's defined as this thing here. So it's the mesh ratio. In the numerator, you again have the fill distance. In the denominator, you have the minimum distance between two design points. And so you can really think of the rho as the ratio between the maximum distance between design points and the minimum distance between design points. Right. So if you want the rho to be constant, then you kind of have to choose what's called a quasi-uniform point set. And so essentially you have to make sure that you don't have points in your design set which are very close together. And if you have points which are very close together, then you get some stability issues. Right. But the main thing to take away really is that we do get this posterior consistency. So if we look at the mean, posterior mean, then that tends to the truth, and the posterior variance goes to 0. You don't need very strong assumptions for this to hold. So in particular, if you have some prior mis-specifications, so the theta aren't really the real theta, or you have to learn the hyperparameters, then that typically still holds as well. Right, so I think there was another question.
Can I ask a question? I wasn't the one probably that raised the hand. I just wanted to ask, because when we look at the previous slide, if we have a bounded input domain, don't you, when you increase n, don't you have the problem that you have increasingly small distance between the neighboring, the minimal distance separating the design points?
So you're thinking of issues with this?
Like this use, right. So if I have a bounded domain and I let my n goes to infinity.
Mm-hmm. Yeah, so this minimum distance would go to 0, but also the numerator would also go to 0. So as long as you kind of have the same rate in both, then
yeah. So right. So is this like something that you proved, or this is like a gut feeling, or?
So I mean, in some special cases you can prove it, right? So if you just have a uniform tensor grid, then you can calculate explicitly what this minimum is and what this supremum is, and then you can show that it really is just a constant.
Okay, thank you.
There are also some results from kind of the quasi-Monte Carlo discrepancy kind of literature. So things like Latin hypercubes and Halton sequences and things like that. There's also some results. So the typical kind of space filling designs. There's also some results that show that this is constant. But in general, you would have to prove it on a kind of case-by-case basis.
Okay. Okay. Thanks.
Yeah.
Ask a question, please. Aretha, the constant C in the bound, does it depend on the dimensions du?
Yeah.
the dimension is kind of fixed because the optimal bound, optimal rate that you showed on the next slide, or yeah, this, if dimensions increases, this would not hold. I mean, there will be some constant that blows up with dimension, right?
Yeah, so this constant here depends exponentially on the dimension.
Right, okay.
Yeah, so that is just, so I mean, that's also what you would expect for this function class. So there are some other results that use sparse grids.
This was my second question, kind of, for sparse grids, do you have the, do you fill the domain? Because the domain is probably filled, but.
Yeah, so for sparse grids, you wouldn't go, you wouldn't use this error estimate, right? So as you say, the fill distance doesn't really, well, I guess eventually it does go to zero. But it's not a good way of measuring the quality. So in that case, you use a different proof technique that is specific to sparse grids. So it's kind of following along the, I mean, it's kind of sparse grid interpolation just with radial basis functions instead of Lagrange polynomial basis functions. So you then use kind of a specific proof technique for that. And I usually have that slide in the talk, but I removed it for this one. So sorry. So in that case, you then get the standard convergence rates that you get for sparse grids. So you get n to the minus alpha for some alpha where the alpha is independent of the dimension, and then you get the log factor, so log n to the dimension.
Okay, what about stability in that case?
Sorry?
What about stability in that case?
Yeah, I mean, you would have similar issues with the stability as well. Yeah, so I mean, essentially sparse grids use this result in 1D, and then you kind of tensorize it to get the higher dimensional one. So you still have these stability issues as well, but it's then an assumption on the stability or on the quasi-uniformity of the one-dimensional rule that you build this sparse grid on. Does that make sense?
Yeah, okay. Thank you probably to my questions. Thank you.
Yeah, no worries.
Yeah, sorry, I just have a follow-up question here, actually about the, so I'm just curious, what if this is the data points are selected using some like optimal experimental design approach, like active learning based on the variance, typically people do this for the GP models. So is there any result, anything you can see in that case?
Mm-hmm. So if you choose the design points randomly and you sample them IID from some measure, then in expected value, this fill distance still has the same rate.
Yeah, so what if they say we have some kind of acquisition function? So for example, people look at the design, the locations to minimize the variance. That's a typical approach, right?
Yeah.
Yeah. So in that case,
I don't know if there are any results specifically for that case.
Yeah, I just think in that case, it's not clear to me if that's actually space failing.
Yeah, it's not clear to me either. So then you would, I think you would have to look, and then also, and I'm not sure if there's any specific results in that direction.
Thanks.
Okay, so that was kind of the first part of the talk. So in the second part, what I wanted to talk about is using deep Gaussian processes as the prior distributions for the regression problem. So we're still doing exactly the same setup as before, that we have our function values on the function f, and then we put the prior on f, and then we get the posterior. Right. So the only difference is now that the prior distribution is not a standard Gaussian process, but it is now a deep Gaussian process. I'm going to start by explaining what deep Gaussian processes are, how you can construct them, and then the main kind of message that I wanted to convey is that these deep Gaussian processes really offer a class of very flexible prior distributions to use in regression, and they work very well. I'm going to show you some examples there. Right. So let me start by just explaining what deep Gaussian processes are. And so deep Gaussian processes are defined through a sequence of functions or sequence of stochastic processes. So we now have this sequence of stochastic processes, FL, and they are defined hierarchically in this way. So the F0 is a standard Gaussian process, as I've discussed before. For simplicity, again, we're using mean zero. You can also do non-zero mean, and you have some covariance kernel. And then the other, so kind of the next layers or the other stochastic processes in the hierarchy are defined conditionally. So the FL plus 1 given FL is then again a Gaussian process with mean zero and some covariance function that depends on FL. Right? So there's very many different ways that you can do this, and I'll show you two examples on the next two slides. But the thing is just that the FL is going to enter into the covariance structure or the covariance kernel of FL plus 1. Yeah? So conditional on FL, the FL plus 1 is just another Gaussian process. You can kind of think of the FL plus 1 as a Gaussian process with a random covariance structure, and the covariance structure is random because the FL itself is random. Okay. So of course, you can kind of include as many elements in this hierarchy as you want, right? So you can define FL for any natural number L. We're going to say that we have a deep Gaussian process with L layers if we kind of have L functions in the hierarchy. So that is FL minus 1. So we're starting with F0. Okay? So it just means that you kind of have L layers or L of these functions that are used in defining the deep Gaussian process. How you choose this number of layers L is a good question. In practice, you often see that you don't really need very many layers. So even though theoretically you can include as many layers as you want, and you might be tempted to include very many layers because you think that, that it's going to give you a very flexible distribution that can model a lot of different things. In practice, you actually see very often that the L doesn't need to be very large. And what I mean by that, it's quite often just in the order of maybe 5 or 10 layers, even for very complicated problems. Right? So there's our recent paper. So this is joint work with Matt Dunlop, who's now in New York, and Mark Girolami and Andrew Stewart. So this joint paper where we kind of give some justification for why you don't need to use a very large number of levels. And again, I'm happy to talk more about that later, but essentially what you can show is that you have a limit that you approach as L tends to infinity. And so at some point, increasing another level isn't really going to change anything very much because you've kind of already reached the limiting distribution. Well, let me now give you some examples. Right? So as I said, exactly how the FL enters into the covariance structure can be in a couple of different ways. So I'm going to show you two examples. This first example is kind of the classical deep GP construction in the seminal paper. So it's based on composition. So it's similar to the construction of deep neural networks, where you use the output of level L as the input to level L plus 1. Okay. So you just have the input of one layer is the output of the previous layer, which means that you have this formulation here. So you just use the output of FL as the input to FL plus 1. That of course works if the output space of FL is the same as the input space of FL plus 1. So in particular, if all of the F's just map from the reals to the reals. If you have a different input space and output space, then you need to include some suitable transformation G that just maps the output space of FL to the input space of FL plus 1. And yeah, what kind of G you use here would again depend on the application. So this construction, as I said, this is kind of the classical deep GP construction. There are some known issues that happen for large, if you have a large number of levels L. In particular, you can see that you kind of converge to just piecewise constant functions. And there are some, but yeah, it's a known issue, and there are there's some recent research trying to mitigate those issues. So if you're interested, there's this paper here. So that is one way of getting the covariance function dependent on FL. Another way is what I'm going to show you here now. So in this example, what we're doing is that we're using FL to define the hyperparameters in the covariance function of FL plus 1. So how does that work? So in particular, what we're doing, so we're using this non-stationary covariance kernel construction introduced in this paper. So you need two ingredients for this. So the first ingredient is a stationary covariance kernel. So there's going to be a covariance kernel that is stationary. So the covariance between U and U prime only depends on the distance between them. And then you have this correlation length scale parameter lambda. Right? So if you want to think of a particular example, you can think about this Maternal kernel, right? So you have this kernel that depends on U minus U prime, and then you have this fluctuation length scale parameter lambda, right? So that is one ingredient. So you have this covariance kernel, and then you have a function lambda that now represents a correlation length scale function, right? So we don't just no longer have a real number lambda, which gives you the correlation length scale and the kind of size, the length scale of the fluctuations. We now want to make the size of the fluctuations non-stationary. So we want to make it dependent on where we are in the domain. So that's going to give us some correlation length scale function lambda of U. So essentially what you want to do is you then want to kind of plug in the non-stationary length scale function lambda into this stationary covariance function to kind of get a non-stationary version of this stationary covariance. And that's essentially what we're doing here. To make sure that you still have a covariance kernel, so something that's symmetric positive definite, you have to include this prescaling factor here. But yeah, it's just a technicality to ensure that you still have a function that's symmetric positive definite. Okay. So what are we going to do for the deep Gaussian processes? For the deep Gaussian processes, we're going to choose our correlation length scale function lambda to come from the previous level. Right? So we're going to use FL to define the length scale of FL plus 1. Yeah. So because lambda is something that's physically always positive, in FL as a Gaussian random field, you have to use some transformation which makes it positive. So quite often use the square or the exponential. But that is really all you're doing. So then the FL plus 1 given FL is just this Gaussian process with this non-stationary covariance function with the length scale given by the previous layer. Right. So I think that's going to be clearer once I show you these examples. So here, each column shows now an independent sample of the deep Gaussian process distribution, right? So each column is just one independent sample. The first row is the distribution of U0. So this is 4 samples of my, sorry, not U, it's F0. So the first row is just 4 samples of F0. The second row is 4 samples of F1. The third row is 4 samples of F3 and so on. So these are really samples of a standard Gaussian process, right? Or F0 is just a standard Gaussian process. And this is the samples of a deep Gaussian process with 2 layers, and then deep Gaussian process with 3 layers. And then in the end, the bottom row is deep Gaussian process with 7 layers. Right? And you can see what I was explaining on the previous slide, that you get this non-stationary behavior, that you have very different length scales, right? So for example, in this plot here, you have this region up here, which is very smooth, and the function is almost constant. So you have quite a long correlation length scale, whereas you have these other parts of the domain where you can have kind of very fine scale features and fluctuations on much shorter length scales. And so you have a lot smaller length scales there, right? So this is the kind of behavior that you then get. And you can see the places at which you get short and long length scale, because the F L-1 here is random, right? So the places at which you have short or long correlation lengths is also random. Right. So let me now just show you some numerical results. So I'm going to skip this in the interest of time, but if you're interested in the algorithm that we actually use to sample from these deep Gaussian processes, let me know. We have an MCMC algorithm. So the problem that I'm now interested in solving is I have this function. So this is now my true function f. And what I'm given is point evaluations of this function. In this case, we have noise in the point values. And we have that at just 50 equispaced points in the domain 0, 1. And then I want to use deep Gaussian process regression. So Gaussian process regression with the deep Gaussian process prior to recover this function. Okay. So this is the output that we get from our MCMC method. Right? So our MCMC method always samples from all of the layers in the deep Gaussian process. The left column is the final results that we get. So these are our kind of final reconstructions of the function f that we want to recover. So this bottom one is the one with just a standard Gaussian process. So technically, that's a deep Gaussian process with just 1 layer. So this is standard GP. The second row from the bottom is the deep Gaussian process with 2 layers. So this is going to be the F1, and this is the corresponding F0. And then this is with 3 layers. So here we have the F2, F1, and F0. And here F3, F2, F1, and F0. Right, so these are the means that we get from our MCMC sampling. Right. So as I said, these are the final reconstructions that we get for a function, and you can see that the standard Gaussian process is struggling because it can't really capture the steep gradients that you have here, and we're doing better as we increase the number of layers. And you can also see that these graphs here are estimating the length scale, or in this case actually the inverse length scale of this function, and you can see that you have these peaks here, so these parts here where you have a very steep gradient, and you need a very kind of small length scale to capture that. You have very large values for the inverse length scale here, whereas the parts where you have quite smooth and you have a very long length scale, you have a corresponding long length scale. Okay. So the algorithm is able to learn that as a part of the inference, where you need a long length scale and where you need a short length scale. Right. So let me just quickly show you this other example. This is exactly the same example, just in 2D. So I now want to recover this function. This is just the corresponding contour plot, and I have noisy point evaluations at about 1,000 points. And these are exactly the same plot. So these are our final reconstructions coming from a standard Gaussian process prior, a deep Gaussian process prior with 2 layers, and a deep Gaussian process prior with 3 layers. And you can see that the reconstruction becomes better. And in particular here, you can see that the 3 layers are able to capture this fine scale features that you have in this region, whereas the 2-layer process is not. Right? So you do get some benefit from including the 3rd layer. instead of just looking at it visually, you can actually also compute the errors. So if you compute the errors between the true function f and the deep Gaussian process with L layers, you can see this is the case where we have 1,000 observations of f. So this are the numbers that correspond to the plot that I showed you on the previous slide. And you can see that with 3 layers, you do get improved recovery. However, there is still the issue with overfitting as well. So if you don't have that much data, so if you only have observed f at about 200 points, then you can see that increasing a 3rd layer can actually give you a larger error again. And that is really just related to kind of the standard issues with overfitting. All right. So as I said, the main thing I wanted to say in this deep GP part is that deep GPs can provide kind of a very flexible distribution, a very kind of flexible prior distribution, which easily can model quite complex functions. And the nice thing about these deep GPs is that it kind of learns everything as part of the inference, right? So this reconstruction here, and in particular these length scales that it kind of learns all of that automatically. So it doesn't have, for example, the issues that treat Gaussian processes have, that you kind of need to specify kind of how many different regions you have and how many different length scales and things like that. But it kind of is able to pick all of that up automatically. If you're interested, here's the main references on the deep Gaussian processes. And for the first part, the main references would be this paper. Okay, thank you very much for your attention.
Thank you very much, Aretha, for the very nice talk. Do we have any further questions?
Yeah, so I just have, actually I have a question about the second part of the deep learning, the deep Gaussian process. I'm just curious, like how it, I just wonder if you have tried with higher dimension problems, how to scale with dimensionality?
So you mean this dimensionality? Yeah.
No, actually, so here you show that, yeah, this is a 2D example, right? So yeah, I'm just curious, like, did you try with higher dimensions, Yeah.
No, I have to say we only had this. Yeah, so just 2 dimensions.
Thanks.
So can I quickly ask, can you comment on the scalability of this Gaussian process regression model? Because I have the impression that if you go to very high dimensions, then it can be computationally quite expensive. Is that correct?
So Gaussian process regression or deep Gaussian?
Maybe both of them, if you can comment on.
Yeah, and what do you mean by dimension? Is it the dimension of U or? Yeah, I mean, so for the posterior, right, you have explicit expressions for the mean and the variance. So the main computational bottleneck is usually this inverse of the
yeah
you have here, right? So that only depends on n, so that it actually doesn't matter what dimension the U is, right? So it only depends on n in this case. So you have to put this in the n matrix, which is usually the computational bottleneck. And then for the deep Gaussian processes, you essentially have to do this for kind of every layer. So in terms of the deep Gaussian process, the cost would scale linearly with the number of layers that you have.
Okay, thanks. So then does that mean that if the capital N is quite large, then it can be quite expensive computationally then?
Yeah.
Okay, thank you. Any further questions?
Yeah, may I have a question on the deep Gaussian process? That my curiosity. So in the construction of deep Gaussian process, it look like the construction hierarchy here. So at the layer L+1, it depends only on the layer L, right? So it's like one step memory. So can you include longer memory, like depend on the two previous one, and would that give a better?
Yeah, so I think kind of from a methodological point of view, you can definitely do that. So I mean, the theory that we did that kind of tells you that you have some limit as the number of layers increases, that specifically uses kind of the Markov
exactly.
Structure. So this theory wouldn't hold. But I mean, in general, you can you could make it dependent on the two previous layers. The only thing that I've seen in that direction is this. So in this paper, the way that they fix these issues that they have for large L is they kind of use the structure of input connected neural networks. So they make the FL+1 conditioned on FL and F0. So they make everything dependent on F0 as well. So it's not quite the same. But that kind of goes in that direction, and they show here that works quite well. So I think in practice that is something that might work well and would be worth doing. But I guess you kind of have to figure out how to do it.
I see. Yeah. Okay. So you mentioned in the proofs you somehow use a Markovian property.
Yeah.
So
in the proof, we say, this is a Markov chain.
Yes. Exactly. That sparked my question. Okay. Thank you very much.
Thank you.
Do we have any final quick questions? If not, let's thank Aretha again. Aretha, if you can stay for a couple of minutes in case someone wants to ask any further questions. And thanks to everyone for attending. Thank you very much.